1.5. You will say me, at a certain moment, you will have eta th higher than 1. No, because don't forget that when you increase the bypass ratio, this is this term that you increase, you are also reducing the VZP. And it will not be anymore 1/2 that you will have there. If it's 1 divided by 2.5, this is the square, you will have here maybe 1 divided by 6. And in fact, when you increase this term is also decreasing a lot. And when you increase this term, we have said that we are also decreasing the PLPC, so this term is also increasing. And so in fact, this is not 1/4 that we have there, but this is maybe 1/5, 1/6, 1/7. But you will see that thanks to the bypass ratio, you increase the thermal efficiency. And you see that in all these parameters, there is one, let's say, leader in the parameters. This is the bypass ratio. Because thanks to the bypass ratio, you reduce the VZP. Thanks to the bypass ratio, you are able to decrease the PLPC. So you reduce the VZS. So you reduce this, you reduce that, and thanks to this parameter, you increase eta th. So you see that the bypass ratio is really helping to increase the eta propulsive and is really helping to increase the eta th. So really helping to increase eta global, that will increase 2 times, and so to decrease the TSFC. And globally speaking, very important drawing that I'm giving now, the TSFC is a parameter that is influenced like this by the bypass ratio. So we start at 0, of course. This is the turbojet. That was 1 kilo per decanewton hour. This is decreasing like this. Decreasing, decreasing, decreasing. And at a factor like 10, this is quite possible, you are maybe at 0.35. At a factor like 12, you can be at 0.3. At a factor like 13, you can be at a factor like 0.28, things like that. Decreasing, decreasing, decreasing. But there is a problem. The problem, we will discuss that later on into more details. This is this. When you increase the bypass ratio, you increase the size of the engine. And by increasing the size of the engine, you increase the size of the nacelle that you have here, of the coal, of the external carter of the engine, between the intake, the section 0, and the section exhaust of the secondary nozzle, the exhaust of the secondary nozzle, that we have not really called, that you could call 5 secondary. So after 1.5, because 1.5 is here, and so this is more the section 5 secondary, and this one is now the section 5 primary. Okay? And so you increase the size of this system. And so by reducing the TSFC, in fact, what you are also doing is that you increase the size of the coal of the secondary flow by going into this direction. And you have, at a certain moment, a kind of compensation. So you increase the bypass ratio, so the size of the nacelle around the low pressure compressor is increasing, 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 Don't forget that we have a surface there. And the surface, this is 2πr, and you need to multiply by the length. And so you are increasing the surface that is frictioning against the air, and this is increasing tremendously the drag due to the surface, the coal that you have, the nacelle that you have around the engine. What can you do? You can try to shorten it, certainly not to extend it until the end. So you have an exhaust there, and you have an exhaust that is at the front only. But even like this, you have a decrease of the TSFC, and you have an increase of the drag due to the nacelle. And these are two parameters that are playing against each other. Because the engine is better, but the engine is introducing more drag. And so this is destroying a part of what you are doing here. This is playing a role in what is called the TSFC installed. I will introduce that later on. This is the TSFC uninstalled, without considering the nacelle. This is when considering the nacelle. And the TSFC installed, in function of the bypass ratio, it will not be a decreasing function as here. It will be a higher value, and this will decrease, and at a certain moment this is doing something like that. So at a certain moment, the gain is becoming marginal due to the bypass ratio, and even the gain could become negative. So it's not a gain anymore, of course, when a gain is negative. That means that the drag due to the coal is costing you more energy than the gain that you have through the increase of the bypass ratio. Of course, globally speaking, we say always that a turbofan is good for the bypass, it's good for the TSFC. It's good for the TSFC. So certainly, the analysis is very different when you look at the problem of the specific thrust. And the problem of the specific thrust must be separated from the problem of the thrust. If you look at the thrust, what is the thrust equation? So we have introduced a new equation for the thermal efficiency. We have also introduced, it was somewhere, a new equation for the propulsive efficiency with the average ejection speed. But we have also another equation for the thrust. The thrust, it was m dot v jet minus VA plus A5 P5 minus PA. It has always been the equation of the thrust. But we are now in a turbofan. So we have a primary flow and a secondary flow. That means that we have a m dot P V jet P, A5P, this is the section here, P5P, and also we have m dot S, V jet S minus VA plus A5S, P5S minus PA. Okay? You need also to compute two nozzle pressure ratio, a nozzle pressure primary and a nozzle pressure ratio secondary. The nozzle pressure primary, this is PT4 divided by PA, and this one, this is PT 1.5 divided by PA. It can lead to different conclusions. The primary can be adapted or saturated, the secondary can be adapted and saturated, and all 4 cases are possible. Huh? It's possible to have adapted, adapted, saturated, 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 adapted, and adapted, choked. Huh? Everything is possible. But normally, these 2 terms are small, compared to what we had before. And we can speak about the thrust. We have 1/2, let's say, of what we had before. This is 1 compared to what we had before. This is also 1/2 compared to what we had before. So this is 1/2 of the thrust I had before. You see that depending on m dot s, the thrust can increase a lot. If you have 6 here, this is 1/2, 6 1/2, 3, 3.5. It's 3.5 more thrust than before. Huge increase of the thrust. Huge increase of the thrust. But not a huge increase of F divided by m dot. Huh? Because you have, let's say, increased the thrust by 3.5 when you take 6. And if you take here the total mass flow rate, the total mass flow rate, it is m dot p 1 time, 6 times, this is 7 times the m dot p. You see that the F divided by m dot has been decreased by 50%. So you can have a look at that when you are trying to sleep. Maybe you will not sleep anymore after this class, but we have really invented a new engine. We have almost done nothing because we have just added a kind of bypass there around. But when you look at the performance, it's very different. We have reduced the TSFC by a factor 3, more than 3. We have increased the thrust very largely, but we have decreased the specific thrust also very largely. And so you see that compared to the turbojet, if you look to our 2 performance parameters, we have a huge gain there, but a very large decrease of the performance here. So very different engine. And so the engine that we have invented here is intended to do what? Decrease the fuel burn. Burn less fuel, burn less fuel, burn less fuel. But certainly not a good accelerator. Because the thrust and the fuel burn are low for the fuel burn and high for the thrust, thanks to the mass flow rate. An engine like this one, you must imagine that the mass flow rate entering into the intake, so the mass flow rate entering here, it can be, in order to give a rough approximation, 1,000 kilo per second. 1 ton of air per second entering here. 1 ton of air, it's maybe not indicating you a lot. But 1 ton, if you take, let's say that 1 cubic meter is 1